Swayam Prabha. Digital India. Educated India.
Now we'll start with this linear systems control design part. This is an important part of any mechatronic system to develop the good controller, which is the brain of mechatronic system. So we'll kind of develop, also we have seen our feedback concept in the previous classes. So we'll now get into a little bit more details about specifically for linear systems how we can go about developing control, okay, and give you some kind of initial background in the domain of control design for mechatronic system in general. Okay, so let's begin with this part. If we see typical systems that we'll encounter in the domain of mechatronics systems is of the kind of rigid body systems or fixed systems with flexibility. Now rigid body systems may have single or multiple rigid body and single or multiple degrees of freedom also. The typical examples could be mechanisms, robotic systems, belt, pulley drive, and so on and so forth. They typically have a limited number of degrees of freedom. So many times you have single or 2 degrees of freedom, although the number of bodies may be different, may be many. So if you take an example of 4-bar mechanism, then it has 4 links, but actually degree of freedom is only 1 because they are constrained to move in certain fashion. And we have seen the kinematics of such motion in the past, in the previous courses. So they may or may not be under actuated. Typically in like all the industrial commercial mechatronic system, they will not be under actuated. They will be having full degree of freedom actuation. Contrary to that, systems with flexibility will have by their nature infinite dimensional systems nature. Okay, so what we do for control is some kind of a finite dimensional approximation by using some methods like there are some method called assumed modes method, or simply assuming like all the elements to be co-located or lumped kind of a mass and springs kind of a approximation. So there are many different ways to do that. These elements typically make the system, the compliant elements, flexible elements, make the system under actuated. Okay, so one can handle this 1 or 2 degrees of under actuation by developing some kind of a nonlinear controllers, so that under actuated systems control is completely a different kind of issue to discuss and handle, especially in the nonlinear domain. Linear domain, still you have some kind of tools to deal with them. We'll see some part something in class. Then there are tools which are available based on the continuous domain model or infinite dimensional model, which is partial differential equation based. This area is still developing. Okay, and of course these are both the cases, like you'll have some kind of a connection with the electromechanical actuator part or a hydraulic actuator part and things like that. Okay, so this is like the main kinds of system that we have. Now this is an important concept that we need to understand upfront here. I'm kind of putting it before we delve into other topics, is concept of feedback and feed forward, so that we can see for practical mechatronic system implementation situations, we may need to consider some advantages and figure out which one of these or both of them together would be better for your application or not. Okay, so we'll see that in a little bit more detail. So let us consider our standard example which we are familiar with: a simple mass moving on a horizontal platform with this force applied is F. and that is our control input. Under this situation, we know the equation governing the system is this F is equal to mx double dot, and the question is, again we have seen already that okay, we are at some position here. From here we want to move to some other position with say some kind of a like given amount of time. So if we want to do that, we can come up, now that we know how to plan trajectory, we can plan trajectory for that much amount of time for this mass going from here to the desired position, and say like a trapezoidal trajectory or sinusoidal kind of a trajectory. So you have a choice to like make a choice there, okay, and then get x desired value. Okay, so at every position where I want x desired to be, and once you have this x desired value available as a trajectory or as a function of time, then we can differentiate that and get x double dot desired. Now when you put that x double dot desired into this equation, multiplying m with x double dot desired, then we get this desired force. Okay, now we can use that force and apply it on this system in time, and by the end of the trajectory, whatever this x double dot kind of becomes 0 again, our block would have moved to the final position. Okay, under ideal scenario where there is no friction, no other disturbances in the system. Okay, that is one of the ways of driving the system to the final position. We are not considering feedback in this case. Remember, we discussed feedback in a lot more detail, but now we are saying we are not using feedback in this strategy. Okay, so now think about, if we do this, what are the problems? Okay, so if we see the feed forward, so this is called feed forward case, okay, where we are just giving whatever is needed for getting to the final position, already planned trajectory, we give that input. Now if the friction is there, the presence of friction will make this not go to the final position. It goes to some middle position, depending upon what is the level of friction that we are dealing with here. In contrast to this, your feedback strategy is a PD control kind of a strategy, okay, with somewhat tuned gains such that we achieve the result in the same amount of time, okay, would overcome these effects of friction, because we are continuously monitoring the error between the current position and final desired position, okay, and depending upon that we are taking some kind of a designing some kind of a control input F. So these two cases, okay, in one case we are doing just feedback, in other case we are doing feed forward. There are some advantages and disadvantages. Can you figure out that? Okay, think about that, and then we'll come to combination of these two effects together in one of the control strategies. Okay, so think about it. Maybe you can list it down and then we can proceed. Okay, maybe you can pause here, and I'm continuing further. So you see that in the feed forward approach, you will apply the input only what is required. Okay, we are not giving any extra input or whatever. Okay, whatever is required, we'll give it, and it will execute the strategy. Okay, trajectory. And drawback for that is, so input will be not really very high or very low. It's just whatever is the amount of input that is required. In the flip side of it is that we don't guarantee to be in the final position, because we are not taking feedback and kind of monitoring where we are. But if you go to feedback case, you'll find that we take care of somewhat the error in this case. However, if you see initial kind of a position to begin with, there is a maximum error between the desired position somewhere here and the current position somewhere here. So the error is maximum, and if you want this to happen in like very small amount of time, then you would tune the gains to have very high values. Now when the gains have higher values, that is multiplying this highest error, then initial control input that we need to give to the system is really very high. Okay, and that many times that input is beyond a level of actuator saturation limit, and that's where like you, although you have planned to go it in certain fashion by tuning your PD control, because actuators will get saturated for some time duration, the job is not really well done. Okay, in the sense we don't kind of guarantee that time, whatever time we had tuned our PD control gains for. Okay, so that's the flip side of feedback kind of a control strategy. So in effect, what we need to have is some kind of a combination of these two strategies. Okay, so what we'll do is we'll give the force which is required to go from here to here according to the planned trajectory, and in addition, now beyond this, even after doing this kind of a feed forward kind of a term, feed forward control application, beyond this whatever we want to control is where we add our feedback control. So feedback control will be just looking at the error between the desired trajectory that we have found by planning and the actual trajectory x or actual position x, and only like if that every time point if it is not matching, you will apply the additional control. So error will be redefined here. Our x desired, which was final position here, is not now considered in PD control. Now we consider the desired trajectory that we had planned. Okay, that is considered to be a final position for the error calculation. Okay, and then you'll find that the error at every point is not so high. It's kind of some small whatever is caused by the disturbances, and that would like minimize, or that would like would not allow the control input to go beyond saturation. So there are many other advantages of feedback plus feed forward control approach. So naturally now since we are only doing like the error difference between this whatever is achieved by feed forward and our planned trajectory, okay, that error is multiplied by gains. We don't need very high gains in practice. Okay, we'll need the typically gain values required will be lower gain values also can achieve the same level of performance. Okay, so because of this gains being low, so gains being low is a good thing for the sake of these other disturbances, that unwanted errors are there, like measurement resolution there will be some error, quantization error will be there, like number representation error, or some kind of a derivative computation error. So these different kind of errors or noises, so to say, are there, electrical noise. So these noises which are undesired kind of effects, they are showing up in a sensor measurement. Okay, or what are the terms that are going in the feedback terms. Now if these terms are multiplied the gains, then these errors also will get amplified. Okay, so since our gain requirement in feed forward plus feedback control are low, I mean the gain requirements low means the gain values are low, the amplification of this unwanted noise will not happen, and that helps a lot in achieving better control action. Okay, so the control in this case will be then because of the lower gains, the response to these errors will not be there, will not be very high, and see, if the response to these errors is high, that will disturb your control objective itself. Okay, so you want to kind of settle into final position, but it will kind of be jittery in the final position because these errors are unnecessarily getting amplified by the gains, and that much input is going anyway to your control. Okay, so this is an important aspect of feed forward plus feedback control approach. So as long as possible, you should try to do this feed forward plus feedback kind of a approach. And also with the lower gains, the control will be robust to any disturbances that the system sees. Now, what are the flip or the cons of this feed forward approach is you'll need more control computations to be performed in the microcontroller. So you'll need a microcontroller which is having more power or more kind of high speed. And then you need to know the system parameters very well, so that you are able to kind of compensate for most of the things you will be able to compensate. For example, if in this case the mass is not very well known, okay, mass is known plus there is some delta error in the mass, so m plus delta m, then the delta m error will be treated by the feedback control. Okay, so feed forward will take care of actual m, but then that error delta m will be handled by the feed forward, the feedback control terms in the control. Okay, so it's good to kind of have the better better the estimation of the parameters of the system, better will be lesser will be a load on feedback term in the control. And then you'll need to identify friction to kind of compensate for friction in the feed forward kind of a way. Okay, so this is an important kind of a consideration. So we'll see many kind of controls that we'll carry out. We try to see whether we are able to apply both of these approaches together to a control system design. Okay, control design basically. Now there are many approaches for rigid body systems, so we will consider mainly the linear kind of a control design for now, and then we'll come to this Lagrangian formulation based approaches. So this form of the equation we'll treat little later by adding friction to it. Okay, right now we'll focus on mainly linear systems approach. And for linear systems, you have these approaches based on the pole placement and classical control tools. Okay, you just need to remember here this but is there to that is a friction that will be there in the system, and many of the approaches that you are taking may not kind of completely represent system in its full sense without friction. So friction, actual system has friction, your model will not have friction. And other thing is saturation will be there in the actuators, that we need to always monitor. So you tune the gains and say, okay, oh, my system is working fine. That's not enough. We need to look at with those gains what is the control input that is required, and whether that control input that is going to the system is exceeding the actuator saturation limits. Okay, so so these are the kind of these are the main approaches that we will take, and then we need to kind of see that in some cases the friction will be too high, in some cases it will not be so high. All those kind of non-linearities need to be handled over and above what we have learned as classical control techniques and tools. So for this typical approach will be first consider system without friction, develop control, and then implement it on or simulation implement it in simulation on a system considering all the non-linearities or all the kind of other things, and see whether it's in the presence of other non-linearities still it is giving the same performance or not, or is the performance acceptable or not, and retune the gains further to get the final kind of controller. That is one approach. Other approach, if that is not satisfactory, then we will have to kind of consider this in the control development itself. So our model itself needs to have these non-linearities incorporated, and we then use some ways to compensate for them. And this is a linear system kind of a design approach, and non-linear system we'll see a Lyapunov based approach. There are many non-linear systems approaches that are available for control, but we will go through only this Lyapunov based approach. That's the most popular one, and many other approaches make use of Lyapunov arguments for its proof, for their proof. Okay, so there are two different parts that we need to think about when we develop controllers. There are, first is like a design issues. What are the design issues that are to be considered when we develop controller? First is the stability. So the way the system is stable, the controller also should be stable. So computation of the control it should be like, you know, from one sampling time to next sampling time, as we are doing this control computation, it should not run away, like, run away kind of in amplitude. Okay, so the control amplitude should be always in control. That means, like, you will have a system controller poles, they should be in the left half of the S plane. Okay, that is our stability criteria. So when we do the controller design, we need to make sure that that criteria is valid. Okay, the controller by itself should be a stable controller. Okay, so we are developing this control to have a closed loop system to be stable, but in addition we want the controller itself to be having some kind of a stable nature. Then we talk of performance of a controller. So it should give the desired performance out of whatever controller strategy you have chosen, should yield you settling time or overshoot in specified limits that the application requires. Then another thing is energy required to achieve performance. Okay, this is very important criteria. Often people miss this out, that you need, like, the energy required or control input required to achieve this performance need to be monitored and make sure that, okay, we are not exceeding these to above the saturation limit of actuator. And then there are implementation issues. In the implementation, you will have two ways of implementation: analog domain and digital domain. So of course here we are talking about digital domain. Analog domain, people are not, right, nowadays these kind of controllers are getting phased out because we cannot change their gains once the circuit is made. The tuning gains and doing some changes in the control algorithms is difficult. And also for the cost, nowadays, because of the microcontrollers available at so less cost, I mean, implementation of this digital domain controller is comparable to in cost to the analog domain kind of implementation, and it provides additional flexibility, additional just change the program and your controller will change, or control algorithm will change. So that kind of flexibility is offered with the digital domain controllers. So you will go for that. Then other implementation issue we have to consider is the sampling time. So sampling time, the main kind of a thing is, like, we need to be able to do the tasks which we are supposed to do in the closed loop, okay, continuously. After every sampling time we are doing this task, or during every sampling time we are doing this task. So this task should get finished within whatever allotted sampling time. If the tasks are not finished, then there is something called overflow will happen, and some of the operations may not be done, and then you will find that your control strategy is not working very well. So we need to design sampling time in such a way that all these tasks are getting completed. What are the tasks we do? We read the sensors, then process the signals of the sensors in some way, if at all, then compute the control, and then implement that control on the actuator interfaces that we have chosen to. Okay, so these tasks should get completed in a reasonable amount of time. So that is one major requirement of sampling time. There are some other requirements, we will discuss them in little more detail, like, as when we talk about signals and signal processing in mechatronics. Okay, so we'll move from here to first type of controllers. Okay, type of controllers, and then we'll see some more linear system control in little more detail. So mainly people use the PID, PD or PI kind of controllers traditionally, and many industries still continue to use them. They work really well in many cases. Then there are these many different types of controllers. Robust, okay, they are robust to internal or external disturbances. Then adaptive, they adapt to the parameters as the system changes, like some properties of lubrication or some other kind of environmental property changes happen slowly. So the system adapts to those kind of changes in by changing the gains automatically. Something of that sort happens in the adaptive control. Neural network control. So there are many different kind of controllers, artificial intelligence based control, deep learning based control, like these are buzzwords these days to talk about. Fuzzy logic is used in washing machine kind of systems. So many different kind of control algorithms are there. Okay, then even the nonlinear controller also is a vast research area. There are several controllers or control algorithms people have paused. I mean, this ever growing area mathematically in this. So there are a lot of developments in this control field, and many mathematicians are involved in these developments, and not all the controllers that you will find in the literature are amenable for practical implementation. So one has to have a wise or wisdom to see, okay, which are relevant for practical implementation and which are not. So that kind of a wisdom we should slowly develop. As we see some of these fundamentals of mechatronic systems, you'll slowly get that kind of understanding. Okay. Now the main design steps that you would consider for development of controllers is basically modeling system. This we have already done, and then representing that model into one of these forms, okay, either differential equation form or transfer function form or state space kind of a form. And then you will select some kind of a control strategy and do some mathematical analysis to establish that, okay, that strategy gives you a stable controller. Then you put some effort into designing the control parameters to make sure that your desired goals of the applications are achieved, and then simulation and experiments, and then reiterate some of these processes to make sure that your final control is good. So representation of system we have talked about already. These are the three forms: differential equation form, state space form, and then transfer function form. Okay, so in each of the forms, you can go back from differential equation to state space to transfer function to differential. I mean, you should be able to convert system into one form to other form, okay, by appropriate mathematical ways. These forms have in each of these forms there are different tools for control available, but we will consider this differential equation to be most fundamental kind of a form of representation, which will give us some physical insight also into the system, and we may use that in incorporating interesting ideas for control. So this is although you may develop some controllers in the state space form, you can transfer them back to the differential equation form to see what their physical aspect or physical implementation or physical insight into that controller is. Okay, so these forms are mainly for the linear systems. Okay, they will not be now for nonlinear systems. Differential equations can be also nonlinear, but we'll be able to convert them into state space or transfer function form only if they are linear equations. Okay. The notions or issues in design and analysis, additional to what we have talked already about, is these are more like a mathematical theoretical aspects. One is like a stability. So there is a bounded input, bounded output stability notion that we have already seen in math class and maybe in some previous discussions. And other important notion is controllability. By definition, controllable system is controllable if it can be taken from one state to another state in finite amount of time. Okay, so this controllability and observability are two definitions that are defined in the domain of state space representation of the system. Okay, so there are some conditions for controllability based on these matrices A, B, C, D of this form. Okay, so we don't get into that right now. We just need to kind of keep at the back of mind that okay, some notion of controllability and observability exists here. If we want to use some control techniques from this domain of state space, then we'll need to worry about these concepts. Okay, so some of you might have already in other classes gone into a good depth of these controllability, observability. You may be free to kind of use them for your project purposes if you would like to, or analyze some of the systems from that perspective and see. So in my opinion, if you develop the design into the transfer function domain or differential domain, you can understand that that's fair enough to go. If you want to, you can design also in this other domain, but I mean it's actually personal choice, I would say. I prefer to kind of choose to not get into the state space domain too much. Actually, I think it's just a personal choice. But I mean you can feel free to kind of get into different domains and look at the things. There are standard tools available in MATLAB for analysis in the state space domain also, and in transfer function domain also. One can use those techniques to do designs. Now we come to this important consideration of pole placement. Okay, so I hope you understand this term pole placement. Pole placement refers to how do you design control so that the closed loop poles will be at certain locations in the left half of S-plane. Of course, we want all the closed loop poles in the left half for the system to be stable. So how do we kind of make a decision of where the poles should be placed given the design requirements or some applications? What are the considerations? How do you kind of do this choice of these poles? Once the choice of the poles in this plane is left half plane is known, then we can kind of see, okay, currently open loop system poles are at what locations, and now if you want the closed loop poles to be these locations, what is the control, how do we develop control? That kind of a control problem can be posed. Okay, then that can be achieved by either using root locus or any modern control or state space based kind of a control techniques. Okay, for example, if the system is controllable, you can place the poles at any locations in the left half plane. Okay, that's a very strong result from the model control theory you get. Of course, that requires state feedback, but still, I mean, by using the state feedback, you can actually design the controller such that you get the closed loop poles at desired location in the left half. Okay, so there are what are the criteria to think about? One is a stability criteria which already is satisfied, but now other criteria is performance, and then other criteria is input requirement. Okay, so if we start performance from performance perspective, we know that if the poles are far away in the left half, then their contribution to the control output is very low, in the sense the contribution dies down fast. So if all the poles are placed far away here, then the response will be very fast for the system. Okay, so we ideally would we will say, okay, look, I want all the poles to be far away as far as possible. That will give me a best response. That will give me a very nice kind of evolution of the system. However, it's not free. things come at a cost. What is the cost that you need to pay? As you push the poles away from the left, away in the left half plane, away from this imaginary axis, then you start increasing the control input that is required to drive the system. Okay, and that is not desirable because our actuators have a limit. Okay, so that's why you don't want to push them too far away. Okay, but you need to have them like enough far away so that it is your performance is good. Okay, so these are fighting against each other, these two things, performance requirements and then input requirement. So that's where if we have strategies which can give you better performance with a little lower control input, they will be accepted, or they will be used in the application much better. Okay, so also that's why from that perspective we may choose to have two poles retained close to the imaginary axis, relatively close, and other can be pushed little apart. So these two poles will be a dominant poles for the system, and output response or contribution to the output from the poles which are far away here, that will be anyway dying down. So we can assume the closed loop system to have only these two poles, like a second order system, and then we can carry out some control parameter design based on the formula that we already know for standard second order system response. Okay, which formulas are also listed here for our utility later. Okay, so that is one of this kind of strategies. Instead of pushing all the poles far away here, we keep retain two poles close to the imaginary axis, and all other poles are a little farther away, so that these poles are dominating. That's the kind of a way one can think about it. So you can do that pole placement or by using this PID kind of controllers, and see now with this controller introduced how the closed loop system poles are and things like that. Okay, so one can start constructing this kind of a block diagram with the flow, and then put controllers at appropriate locations. Your controller may be here or controller may be here. At some location controller is there, then you can analyze the different proposals and see which one is best suited to give you the desired kind of a response. Okay, and typically you will avoid to carry out pole zero cancellations by using controller. Okay, so as some part we know, or if we cancel the poles, especially in the left half of the plane, this cancellation is not really going to be exact, because actual system and its model will have always some small differences here and there, and then only that small part which is not compensated completely, that will kind of have some undesired effect on the system, and it may not work well. So that's why from that perspective we don't do the cancellations here. Okay, so there are a lot of techniques that you might have studied earlier: root locus, board plot, Nyquist plot. These are like the classical Laplace domain control techniques. Then you have the state space based designs, which is based on the linear systems theory. Then in the nonlinear domain you have this Lyapunov control, singular perturbation and feedback linearization, or many different approaches. I am listing only few of them here. Out of that also we are not going to consider a lot of things for discussion. I will give you some kind of a flavor of how do we go about designing and analyzing, and maybe you can use one or more of these techniques to kind of do this final goal for whatever system that is under your consideration. You can make use of this in your project, for example. We'll go through a little more detail in Lyapunov method and what is the best controller that can be possible for a rigid body nonlinear system. Okay, so up to that we'll do, and that is a good controller for practical implementation aspects. as practical implementation as well, so that will be nice for us to look at. Then we will consider now example of linear or nonlinear system. So the system which is nonlinear to begin with is pendulum system. We all know it is nonlinear if you consider this theta for the pendulum to be not small, and then see what kind of a ways we think of its control. And then another example, flexible belt drive system that you modeled in the assignment problem. So I would like you to kind of do this analysis. For that, model is already existing with you, so you think about, suppose I want to position my load at some specific position, and I give input as motor angle or motor torque or whatever you want to consider, and I want the vibrations in the belt to be minimum, okay, or I want to position it the output theta L at some position so that there are not much of a vibrations when I go to the final position. Okay, so how do we kind of develop such a control for flexible belt kind of a system by using some of the concepts of this linear systems theory? Okay, so I would like you to kind of give a thought to that before going further into the discussions. Okay, so I'll pause here for the first video for this part of the lecture, and then we'll continue in the other video for the more discussions on these examples. Okay, so let me stop here.